Hello everyone. My name is Jong-Hyun and I'm PhD candidate in the University of Arizona. The title of talk is Fully Automated Wireless Capacitive Strain Sensing Node Development for High Sensitive Large Area Strain Monitoring. This study is a part of collaborative research project with the University of Arizona, Kansas, South Carolina, and Iowa State University. Structural strain response is one of most widely used measures for structural health monitoring. Because of its high accuracy in measuring both static and dynamic characteristics of structures, and its low cost and easy to installation features. A conventional strain sensing method is to use foil-type resistive strain gauges. However, the resistive strain sensing method have critical limitations in sensing of mesoscale components due to their small sizes, typically a few to tens of square millimeter. With small size sensors, it is not easy for accurate global deformation reconstructions. Therefore, many large area sensing technologies have been developed. Soft elastomeric capacitor, sensing sheet, and carbon nanotube sensing skin, and so on. They has large area coverage representing much better mesoscale structural behaviors. Particularly, soft elastomeric capacitor called SCC developed by the Iowa State University team is a flexible skin type large area capacitive strain sensor. SCC is very flexible and sensitive, which is suitable for high precision structural health monitoring applications. SCC is mechanically robust, low cost, easy to fabricate, and the shape and size is customizable. In the former study, SCC's linearity was validated up to 20%, which is very robust. Right video clip shows a large area deployment of 40 SCCs on the fiberglass plate. Both directional strain along the x and y axis were able to characterized. The SCC showed a global strain field assessment capability with excellent coverage and resolution. The SCC was also employed for fatigue crack monitoring on the steel bridge on the traffic node. The SCC arrangement showed great capability to monitor distortion-induced fatigue crack. The conventional strain gauge requires a resistance sensing mechanism. So, majority of wireless strain sensing hardware have been developed based on the resistance sensing basis. For example, a strain sensing board for Mica 2 and a fully automated and high sensitivity strain sensor board for IMO 2 were developed. However, the SCC is a capacitor which requires totally different sensing mechanism. Recently, our research group at the University of Arizona team developed a high-sensitive capacitive strain sensing node for wireless structural health monitoring. The developed sensing node showed high-precision capacitive strain sensing capability, outperform commercial capacitance sensing circuit. In here, I'll explain about basic signal processing procedure for the capacitive strain mechanism. The capacitance sensing requires the DSOT bridge scheme, which consists of two resistors and two capacitors. 32.768 kHz high-frequency AC signal was fed to DSOT bridge. The DSOT bridge has two sides, which are reference side shown in the blue signal and sensor side shown in the red signal in the video clip. Only the SCC side signal amplitude is changes according to the SCC strain variation shown in the red signal. Two signals are fed to differential amplifier to catch the SCC signal's amplitude variation, and the difference shown in the green signal is amplified for the maximum sensitivity. After that, the amplified signal was enveloped using demodulation circuit and low-pass filtered for output. The DSOT bridge-based capacitance sensing method has several advantages for wireless sensing applications. It has high sensitivity but requires low power consumption and low cost fabrication available, and it can be easily used with any sensing platform, and low voltage operation is available. However, it requires precise manual bridge balancing, amplification, and shunt calibration procedure before use, which are not easy for majority of field engineers. So, we investigated to automate the bridge balancing, amplification, and shunt calibration procedures. And several practical challenges are found. For wireless structural health monitoring application, low power consumption is necessary as the solar power is mostly used for the wireless sensor node. The key challenge of automation of the DSOT bridge circuit-based capacitance sensing system is the control of 32 kHz high-speed sine signal that may require high-performance microprocessors. In this study, We developed an alternative way to control AC signals using an 8-bit low power and low cost microprocessors. For hardware development, we considered the high sensitivity to catch microstrain level sensing, and operation under 3.3 volt to be worked with a state-of-art smart sensing platform X-Node. X-Node is a next-generation wireless sensing platform developed by the University of Illinois team. It has various powerful features such as dual-core processing, 24-bit high-resolution ADC, up to 1 km range radio communication, AWS cloud data management, LTE communication, and also work with various softwares in Illinois Structural Health Monitoring Project software toolsheet. The main contribution of this study is that we developed a hardware-software system capable of automated bridge balancing, amplification, and shunt calibration for capacitive strain sensor with 8-bit microprocessor. ATmega328P-AU was used for microcontroller, well known as the microcontroller in the Arduino Uno. It is basically designed to work with 5V 16 MHz operation. However, we downclocked this to 8 MHz to work with 3.3V with lower power operation. This is full schematic of signal processing procedure. Analog potentiometers are replaced to digital potentiometer AD5254. The manual shunt calibration switch was replaced to digital switch. 2 bridge signals and 2 amplified signals were processed using peak-picking circuit and fed to 16-bit ADC for precise control. This is key part of new circuit enables to control high-frequency AC signal using 8-bit microcontroller. The circuit has 4 32 kHz sine signals that 2 in desorted bridge and rest of 2 in the 2 amplification stages. Feedback loop peak-picking circuit with LTC6244 OPM was used to catch the peak of the sine signals. The video shows that the blue signal is 32 kHz sine wave and the yellow signal is a peak-picked signal converted to DC component. Then, the peak voltage values are fed to 16-bit ADC and microprocessor to monitor the peaks of the sine signals. By using the peak voltage measurement, an automated desorted bridge balancing algorithm was developed. The optimal desorted bridge balancing requires minimal amplitude and phase difference of signals from reference and SCC side bridge. The video shows that what is the best bridge balancing. When the phase matches perfectly, the amplitude of amplifier signal is minimum, shown in navy color sine wave. We utilize this information for optimal balancing. Using digital potentiometer, we control the SCC side signal and measure the variation of the peak amplitude of first amplifier. You can find convex point which shows the best balancing setup. After that, the amplification level was adjusted to maximum possible gain level. For accurate capacitive strain sensing, the two-step shunt calibration was developed to eliminate parasitic capacitance effect of the wire. The figure shows a sensible measurement output of the bridge balancing and two-step shunt calibration procedure. Shunt capacitors were set up as 1 picofarad and 3 picofarad to make 2 picofarad difference, and the two peaks around 10 to 25 seconds shows the voltage variation accordingly. With current setup, we found the calibration factor as 45 mV per picofarad. This is the prototype PCB board. The figure shows the assembled sensor board and each circuit location. To validate the performance of the developed system, a shear building test was conducted. NIDAQ was used for the sensor board output measurement and reference strain measurement. Last year, Iowa State University team developed a textured SCC which has better resolution and sensitivity and linearity. It has higher gauge factor than non-textured SCC showed better sensitivity. Also, it showed capability of low cycle fatigue crack detection capability. A steel plate Spiceman was fabricated using a new textured SCC and strain sensor shown in the figure. We tested 1 Hz and 3 Hz cyclic sine excitation test. The test was conducted after the automated balancing, amplification, and shunt calibration. The sensor board was able to measure the dynamics with amplitude variation very well. The signal shape from sensor board measurement looks a bit noisier, but that's because the large area sensing reflects the mesoscale behavior of entire sensing area than very localized dynamic deformation from the strain gauge. So, I want to conclude this presentation by recapping what I presented. A fully automated capacitive strain sensing hardware and software was developed. Peak detection circuit module was deployed for high-frequency sine signal processing with 8-bit microprocessing unit. We developed an automated bridge balancing, amplification, and shunt calibration software. A prototype hardware was developed, and we validate the hardware software system using textured SEC via shake table test. The developed sensor board was able to fully automate bridge balancing, amplification, and shunt calibration procedure. We acknowledge that this work is supported by the Transportation Pooled Fund study, with several DOTs including Kansas, Iowa, South Carolina, and North Carolina. Thanks for watching.